Welcome to the ChemDoctor. This is the third video in the series on molecular geometry, which involves drawing Lewis formulas of various chemical compounds, identifying the geometry or the shape of the molecule, and then determining or ascertaining the approximate bond angle between the atoms. What I want to accomplish in this presentation is I want to look at specifically at some of the exceptions and address those particular issues. So the first thing that I want to do is deal with the molecules that have sp3 hybridization but are pyramidal or trigonal pyramidal. So to go back, all right, so we're going to start with a molecule that I already drew in the second video that I did in this area, and what I want to do is quickly review the structure of ammonia. Alright, so here's the formula. Now, as I stated in the last two videos, it's really important that you have strong Lewis formula abilities here, and if you're not drawing structures, you need to exit this particular video and practice drawing structures before you come back to this, because I don't have the time in this presentation to go through the rules on how I get to the structures. So starting with ammonia, its Lewis formula is going to look like this. Most people will end up drawing some version of what I have here. Notice that there will be an unshared pair of electrons on the nitrogen. Now over here on the right, what I've done is I've actually provided a model of what this compound looks like, and you can see that in the model that what's shown are only the atoms and how they're connected to the central nitrogen. The unshared pair of electrons is not here. This structure is called pyramidal or trigonal pyramidal, depending on the textbook and the teacher or the professor and so on. I call the thing pyramidal. I'm pretty old school in this area. Now, the bond angles of this particular molecule are 107 instead of 109. So that brings me to the hybridization. So I want to address this issue now. We started out learning about drawing tetrahedral structures that were sp3 hybridized. So down here in the bottom, what I'm going to do is quickly put up methane. Right, and methane is a molecule that looks like this. When we draw the formula on a piece of paper, we've got a central atom that's bonded to four other atoms. And when we determine the hybridization, we count up the total bonding units. So there's 1, 2, 3, 4 bonding units here, and we subtract 1 to get the hybridization. And the way that I teach determining the shape of a molecule is to first get the hybridization. You have memorized a particular shape that goes with the hybridization, which in this case would be tetrahedral, where each of the bond angles is 109.5. All right, now the hybridization, in fact, doesn't give us the geometry directly, because geometry is based on the connectivity between this central atom and the external atoms that it's attached to. The hybridization gives us the electronic arrangement of electron pairs around the central atom. And you may be sitting there going, well, what's the difference? Well, the difference is actually staring us in the face up here on this example. In the case of ammonia, you see there's actually only 3 atoms that are attached to the central atom here, and then there's an electron pair. The hybridization is still sp3, like it is in a tetrahedral molecule, because the electron pairs are actually arranged in a tetrahedral network around the central atom. But there are only 3 atoms attached to the central atom, and the shape of the molecule is based on the arrangement of the external atoms and how they're attached to the central atom. Now, I mentioned that the bond angle here is not 109.5, and in fact for ammonia it's closer to 107 107 degrees. And I say closer because bond angles are not exact things. It's going to depend on the bond angle in a particular molecule is going to depend in part on what or who the external atoms are and what their electronic density is, right? How many electron pairs they have around their particular center, and how large this particular atom is. And the bond angles then are going to depend on how all of these different atoms are interacting in terms of their electronic environments. And one thing that the student needs to understand is that electron pairs themselves need more surface area to spread out in, because you've got two particles that have the same charge on them, so there's a net repulsion. They're sharing a molecular orbital, which means their spins have to be opposite. So going back to basic atomic structure, remember that if you've got two electrons that are sharing an orbital, they have to have opposite spins so that their magnetic force of attraction is offsetting the net repulsion between the two particles. And in the case of an unshared pair, like we have on many different types of molecules, in this case my model is ammonia, those two electrons only have one nuclear center that they're next to that's functioning to attract them, instead of, like in the case of, if you look at the two electrons that are in the bond between the hydrogen and the nitrogen, the two electrons that are in the actual bond here have two nuclear centers to offset the repulsive effects between the two electrons. All right, or the two nuclear centers are offering attractive forces on the two electrons that are in here, whereas your unshared pairs don't have that. They only have one nuclear center that they're operating in, so, or operating with. So this unshared pair of electrons is going to spread out, and it causes bond compression on the bonds that are underneath them. So the bond angle between the respective hydrogens here does not remain at 109. It's actually less than 109. All right, so moving on from this, looking at some other examples. One molecule that I definitely want to address, because I've actually seen mistakes in not only in textbooks with this, but in the handouts that are quite frankly offered up to students. So notice that phosphorus is directly underneath nitrogen. So if we go to draw this structure, we're going to end up with something that's very similar to ammonia. And we would draw this way. All right, now, generally speaking, again, if I do the hybridization here very quickly, it's going to be 1, 2, 3, 4. There's 4 bonding units. We subtract 1, so very quickly the hybridization is sp3. But this is not a tetrahedral molecule. This is one of our sp3 derivatives. It's similar to ammonia in its structure, so we would call this molecule pyramidal. All right, and technically in these days we would probably call this trigonal pyramidal, to be consistent with the more modern textbooks and so on. The bond angles here are not 109.5. I repeat, they're not 109.5. And more than likely the bond angle is not 107 either. The reason being is because phosphorus is a considerably larger atom than nitrogen. So remember your size issues, right? As we move down a group, the atomic size of the atoms increases, and because of this, how the mixing of the orbitals between the hydrogen and the phosphorus is going to be also slightly different than for the relationship between the hydrogen and the nitrogen, and the bond compression that's going to happen here is going to be even more extreme than for the nitrogen. All right. Now, what does this translate into? On the internet this morning, I went through and I looked in several different locations for the bond angle of this, and what I found is that the bond angle. All right, so let's come down to brass tacks here. The bond angle here is going to be less than 107. It's definitely less. Excuse me. It's going to be definitely less than 109, and I saw I saw estimates that went from about 104 all the way down to approximately 90 degrees. Now, the reason I'm bringing this up is because you need to realize that this unshared pair of electrons up here is causing compression of the pyramidal structure of the hydrogens below it. And since hydrogen is essentially it's a small atom by comparison to the nitrogen, it's going to cause a more acute angulation of these things. And the main take home is that, because quite frankly, I can't find any one source that's saying it's 90, and I can't find any one source that's saying it's 104, but definitely this bond angle is what we can say is that this bond angle is absolutely not 109.5. So I'm going to put that in words because I'm very adamant about this. And even for my own students, I don't want to be reading this on exams or quizzes. It's absolutely not 109.5. And if you're in ownership of a handout that states that pH 3 is of that bond angle, you need to address that with your teacher or your professor and be very careful about this. The bond angles of pH 3, or actually to use its name, phosphine, are no doubt less than 107, and probably in this range down in here that's somewhere between 104 to 90 degrees. All right, now I also want to come over here and address the issues that are like water. So remember that water is a similar type of situation. If we look at its Lewis formula, we can draw a rendition of it this way. It has no less than 2 unshared pairs of electrons on it. When we do the hybridization, it is indeed sp3. Now, again, I want to emphasize what that means is that the electronic arrangement of unshared pairs and bonding pairs of electrons is sp3. But again, the geometry of the molecule is based on the connectivity, and we call this molecule a bent molecule. And its bond angle is not going to be 109.5. It's absolutely, again, not 109.5. It is going to be less than 109.5. And in terms of my own students, I give the bond angle. This is going to be somewhere in the neighborhood. Somewhere in the neighborhood of 104.5. All right, now oftentimes I get asked this question, all right, well, is it exactly 104.5? Well, again, you know, it's going to depend on what the atom is that's attached to the oxygens. All right, and remember, hydrogen is a very small atom. It doesn't have unshared pairs of electrons on it, and so the bond angle between the hydrogens in a water molecule are pretty close to 104.5. But if we switch these atoms out for something else, like let's say that we looked at a structure like this, OF2 for example, it's going to have a Lewis formula that you draw that's going to look essentially just like a water molecule. We still have our unshared pairs of electrons here. And then on the fluorines, there's going to be, we're going to have a total of 3 unshared pairs so that we have 8 electrons around it. Now, you want to use some common sense here. There is a lot more electron density around these fluorines than there is on a hydrogen. And so you would expect this bond angle here to not be 104. But it's also not going to be 109. And what is the bond angle going to be exactly? Well, I don't know off the top of my head, all right? What I do know is that these unshared pairs of electrons influence this electronic environment, have the effect of compressing these bonds downward, all right? By the same token, the unshared pairs of electrons here that are on the fluorines are going to conflict across this region here and essentially operate by providing a force pushing back upwards. So the bond angle in this molecule is not going to be, again, to emphasize 109.5. It's not also going to be 104, but it's fair to say that it will probably be X greater than 104.5, but X less than 109.5. It's probably going to be, well, it'll definitely be somewhere in this range between these values. All right, and with that, I think I'm going to go ahead and close the video, and I hope this helps those of you that are struggling with the idea of unshared pairs of electrons. The key thing to remember is that when you have unshared pairs of electrons, they operate by compressing bond angles. All right, and so the bond angles are not going to be what you would expect in a molecule that instead in these positions would have an atom. And with that, I would like to thank the viewers for watching my presentation. You can find more videos at www.chemdoctor.org, and thanks again for watching.